Hello and welcome to Prog Sweden. We are finally back after our summer vacation, so warm welcome. Prog Sweden is the meetup where we explore functional programming, as you might understand from the title of the meetup and stream. Welcome to all recurring members, guests, and subscribers of the channel, and also warm welcome to everyone that's new in Prog Sweden, watching this for the first time. Let's head over to today's agenda. On the agenda of today, we will have first a presentation by, not a presentation, but a short introduction by me. I will talk about some fun stuff and some other stuff. First presentation is Rust versus F# by Johan Olsson. That I know a lot of people want to see. And then we will also have Turn Old into New, moving to Elixir feature by feature by Anita Luderman. Also very interesting. I know that this presentation is good. And then in the end, if you have more questions you want to ask or more things you want to wonder about, head over to Discord and join the post-show chat. But before we get started, I would like to first thank Beat for sponsoring this video stream and this meetup. If you want to know more about Beat, head over to their webpage, adabeat.com, or check them out in social media. Then FuncProConf 2025, October 15th, we will run a half-day in-person event in Stockholm with 3 great presentations in functional programming. So if you want to come and check out and hang out with other people in Stockholm in October, when it's bad weather outside, come inside, join the half-day meetup or like half-day conference instead in October. Then if we look at the schedule for the coming fall, then next meetup, 23rd of September. We planned for that. We're going to announce it on meetup page also. Then 15th of October, we'll run the FuncProConf. Then 11th of November, we will be at Kivra. That's already in the meetup page. So if you want to join the in-person event on the 11th of November, make sure to head over to meetup and join already now. And of course, if you want to support Prog Sweden, join the group, meetup group, and make sure to subscribe on our YouTube channel. And also make sure to join the Discord to ask more elaborate questions. Which brings us over to questions. So if you have any questions during the presentation, please shoot them in the YouTube chat or in the Discord server. In the Discord server, you can ask longer questions. The YouTube chat is unfortunately a bit limited in size. So with that, let's get started and warm welcome Johan Olsson to Prog Sweden. Hello Johan and
Thank you.
welcome.
Hello.
Hello.
Thank you for having me.
Yes, you're warm welcome, and I know you've been working, you're a long timer within software development. You probably started working with software maybe around the time I was born.
Yeah, maybe.
Yeah.
I started, my first job was in 1990, I
Oh,
think.
yeah.
But I started coding way before that, like in 83 or something like that.
Yeah. Yes, so warm welcome, Johan, and let's kick off your presentation.
Yes. All right. You can see my screen, I hope.
Yes. Yeah, we do, Johan.
All right. Rust versus F#, or the borrow checker meets the pattern matcher, or memory safety versus functional magic. What differs, what are equal? We're gonna take a look at what, no, it seems like it's the same show. Let's share that one. All right. This is all right. You see my screen now, the crab and the wizard?
Yes, we do.
Yeah. F# versus Rust. Who will win? We're going to take a look at what Rust is. We're going to take a little look at what F# is. We're going to compare what those two languages, what are the similarities, differences, strengths, weaknesses. We're also going to have a short discussion on when would you choose one over the other. And my name is Johan Olsson. I'm a consultant at TheTribe in Malmö, Sweden. A small consultant firm. We are about 12 people now, I think. And I'm currently working at Schneider Electric in Lund, where I do Rust programming, a bit of Golang, and a bit of .NET as well. And I have always had a passion for functional programming. And I have been a professional software engineer for 35 years now. And as I said, started coding back in the dark ages, the early 80s. And first, a disclaimer. I am not a Rust expert. This presentation is based on my experience as a F# programmer learning to write Rust. So it's my opinions and my experience. And I might get Rust wrong in some places. So just so you know. What is Rust? Well, Rust was released in 2012. It's built on C++, Cyclone, Haskell, and OCaml. C++, I think you know. That's very, very common. Cyclone is a C dialect with stronger memory checking. Haskell, a pure functional language. And OCaml is a multi-purpose language. Rust is strong typed, and it uses a memory model where you have ownership of memory, and you can borrow memory from other places, and you also have lifetimes defining how long memory should live and so on. We will look into that as well. Rust says we have fearless concurrency, and that is supported by the memory management model. Rust compiles to machine code, it's cross-platform, it's high performance. It's mostly used for system programming, and it's imperative functional language. If we look at F#, that was created in 2005. It's built directly on OCaml. It is also strong typed, but it uses a garbage collector for memory management. And there's a big difference. It compiles to and runs on the .NET runtime, which means it has the .NET garbage collector. And it also uses the .NET threading and async await system. F# is a functional first multi-paradigm language, meaning that we prefer to write functional code in F#, but you could write object-oriented as well if you like. Typical use cases for Rust is low-level system, embedded systems, performance-critical apps. And for F#, it's more data science, finance, web apps, domain modeling, big data, stuff like that. And this might seem to be two very different use cases. And they are. But there are some commonality, there are common ground around these languages, is that they are both strong static type systems, and they both have functional programming support. They both have a very strong concurrency and safety model. They're cross-platform, and both emphasis on correctness. That means that if it compiles, it works. The compiler won't let you do the stupid stuff. And that is something I have experienced compared to object-oriented languages or other languages. There's a whole category of bugs that just disappear when you use a language like Rust or F# because you can't do it wrong. The compiler forces you to handle all cases and stuff like that. If we take a look at the basic syntax, Rust uses curly braces to mark start and end of a block, just like C++. And it uses a semicolon to end a statement, also C++. And type declarations are required in your functions. Whereas in F# we use indentation to mark start and end of a block, just like Python. We use new line to mark end of statement, and type declarations are optional. You don't need that if there is no ambiguity. If the compiler can find out what it is, then you don't have to have type declarations. Common for both languages is that the last statement in a function is the return value, always. Here's an example of Rust. Here we declare a function add. It takes two parameters, x and y. Both are 32-bit integers. The function also returns a 32-bit integer and just adds those two values together. And there is no return keyword here. The last statement is the return value, and there is only one statement in this function. Then in the main function, we call this add with two parameters, 5 and 6. We get the result, and then we print it on the screen. This is a very simple Rust, but you see the curly braces, we have semicolons. It looks C++-ish. If we do the same in F#, we declare a function add that takes two parameters, x and y, and just adds them together. Notice here that we don't have type annotations. We don't say that x and y are integers because the compiler can figure that out for us. This does not mean that F# is dynamically typed. It's not. But in this case, as in the main function, I call add with 5 and 6, which are integer constants. That means add function must have integer parameters. Otherwise, this would not compile. So the compiler says, okay, you're calling it with int, then it must be int. It cannot be anything else. And here's the exact same thing. We add the 5 and 6, and then we print it to the screen. This entry point, that's the .NET runtime saying that you must declare a function to start the program. And we must also always return an exit code, an integer. So 0 on the last line is the exit code of this program. Right? Both languages have immutable by default. So you declare a variable and you cannot change it. You have to explicitly mark the variable as mutable if you want to change it. The compiler will tell you if you try to change something that you cannot do. An example of this is like in Rust, we can declare x as 5. We can print it. And then we try to set x to 6. We will get a compiler error saying you cannot assign twice to immutable variable x. So you can't do that. So what if you want to do that? Well, then you have to declare x as mutable. This means that now you can change it and the compiler error goes away. We can do the same in F#. We declare the variable x, set it to 5, and then we change it to 6. And here we will get a warning because this is not an assignment. X equals 6 is not an assignment in F#. It's an equality check. We are doing here, is x equal to 6? It's not, it's 5. So this will result in false, and we are not using that result. So the compiler says, yes, you can compare x with 6. It's pointless because you're not handling the result of that comparison. Shouldn't you do that? So F# compiler is a bit more forgiving, perhaps. If you want to do this in F#, you will have to declare the variable as mutable, and then you will have to use the special syntax of a left arrow that's saying, yes, I am aware I am putting 6 into x. I'm really changing that, because if you just say equals, that's a comparison, not an assignment in F#. Right? Memory management. In Rust, each value has one owner, one and only one owner. And when the owner goes out of scope, then that value is removed. In F#, we're using the .NET memory model. That is, we have a garbage collector. So when a value goes out of scope, nothing happens. The garbage collector will find that this value is not used anymore and remove it sometime in the future. We don't know when, but it will do it sometime. If we have a value that implements the iDisposable interface, then we can explicitly declare a scope, and when that scope goes out, then that value will be disposed, that is, removed. I will show how that works. But first, Rust, memory ownership. Here we first declare a string, S1. It's a string allocated on the heap. S1 is the owner of this string. And then we set S2 equals to S1. That means we're transferring ownership of the string to S2. S2 is now the owner of the data. If we try to use it, S1, we will get a compiler error saying that the borrow of move value is the ownership is S2. S1 does not have ownership of this anymore and cannot use it. So what we have to do is use borrowing. Here we create the S1, the string hello, and then we want to calculate the length of that string. Then we can say that function length can borrow my string S1 by adding the ampersand. That means you can borrow my string, but you cannot change it. It's read-only. It's immutable. The calculate length function can do what it's doing with strings. It gets the length of it and returns that. And then we print what we got from the calculate length. So S1 is still owned by S1, and it's temporarily blended out to the calculate length function that borrows that string. And returns the when it returns, the borrowing is ended. And this is enforced by the compiler, so it's not in the runtime, it's a compiler check. Another thing is that we can transfer ownership to someone else. Let's say we have this data that is a vector of 3 numbers, and we want to transfer ownership into another thread. Here I'm starting a new thread, and data is transferred, moved into that thread. So that thread takes ownership of that data. If I want to access data after this, the compiler won't let me because I have moved the ownership to someone else, to the other thread. And there's also another thing called boxing. You can box things, that is, you can allocate memory on the heap with something in. Here's I allocate a box with an integer inside. And if I want to access the value of that box in the last line here, I have to use the star as give me the value of that variable. Here we see the C++ thing going shining. We have stars before that. We have also here the ampersand. So it's references, it's pointers, but the compiler enforces this for us, so we shouldn't be able to make mistakes. Right? If we look at F#, there's not much to say about the memory itself. The garbage collector will get it when we it's laying around, not used anymore. But we have this scope that if the data we have implements dispose, and we want to use that, then we can declare a scope by having the use keyword. For example, here we create a text file, and a text file implements dispose. And once we are done with writing data to this text file, we exit this function. That means the scope ends, the file will be disposed, it's closed and removed from memory. And that could be good because we don't want to keep files open, lying around. Well, don't know when it will be closed. We want it to be closed when we exit this function. So we could call file dispose directly in the code, but it's better to use because if an exception handle happens or some other errors, the file will be closed anyway. Right. Data types. Rust declares mainly 2 data types, enums and structs. In F# we have discriminated union and record, but they are the same thing. They're same, different name. They are exactly the same thing. In Rust, we can declare a struct, a rectangle with width and height here. We can add functions to that rectangle, and here's an area function that calculates the area of that rectangle. We can use that rectangle. Here we declare a rectangle with 30, height 50, and then we call rect.area to get the area of that rectangle. And we can do the exact same thing in F#. We declare a rectangle with width and height. We add a area method that calculates the area, and we use it same way. Declare a variable rect width 5 and 10 here, and we call rect.area to call that function. Same thing. In enum, Rust has an enum type, and that is a type that can have a limited number of values. In this case, we have version 4 and version 6 of IP addresses. Those are the only two values that can exist. But what you also can do in Rust is that you can attach values to your enum. In this case, we have version 4 that has 4 8-bit unsigned values attached to it. And then in V6, we have a string attached to it. We can have different values attached depending on what version we are using here. So if we want to use a version 4 address, we can attach the values 127.0.0.1. And if we use a version 6, we attach a string. And this is very powerful. In F#, we can do the exact same thing. We declare a type which has two different values, version 4 and version 6, and we attach values to those. And we use it the same way. Version 4, 127.0.0.1, or version 6, ::1, a string. Now, this leads us to missing values. How is that happening? Well, in Rust, null does not exist. We use an option enum instead. In F#, well, null exists because we are running on the .NET ecosystem, the .NET runtime, and null exists there. But as F# programmers, we really prefer to use the option value instead. But we need to handle nulls sometimes. So what is the option enum? Well, it's an enum that has two values, some and none. So we can use it like this. We declare a value of type option int32 and set it to sum42. So this value has the value sum42, and no value has the value none. And then we have to match, and it's an advanced form of if statement, really. If the value is sum, then we can print it. If the value is none, no, then we don't have a value to print. We print no value instead. And when we do a match, the compiler enforces us to cover all cases. So we can't miss a case here. The compiler forces us to always use that. And we can do the exact same thing in F#. We declare a value of int option. Option is a keyword in F#, but it is the same thing. It's implemented as the enum in Rust, two values, sum and none. Works exactly the same way. We can match on that. If it's sum, we can print that. If it's none, we don't have anything to print. So exactly the same thing. That brings us to pattern matching. Both languages have strong pattern matching capabilities, and you can match them a lot of different things, values, ranges, data structures, etc. And both languages use exhaustive matching. That means that the compiler will complain if you do not cover all cases. F# also has an active pattern feature that Rust is missing, as far as I know. I will show that. So in Rust, we can compare or match on a range. We have a value 5, and we can match if it's 2 or less, if it's between 3 and 10, or if it's 11 or bigger. That's very powerful. A lot of variants you can do on this. And we can do the exact same thing in F#. Looks almost identical. Small details in syntax, but looks exactly the same way. In Rust, we can match on a struct. Say we have the variable rect. It's a rectangle, and we can match on if the width is greater than height, then we have a wide rectangle. If width is less than height, we have a tall rectangle. If they are equal, then we have a square. And then the compiler enforces us to have the other case, the catch-all case, that we don't know neither of these ifs fall out. So we have to do a third or fourth case where none of this is true, which should never happen really, but we have to do it. And we can do the exact same thing in F#. We match on the rect. We have its width and height. And we use when here instead of if, but it's the same thing. Width larger than height, we have a wide rectangle. If width is less than height, then it's a tall. If they're equal, then it's a square. And we also have to do the fourth case when none is true and say we don't know what this is. So record it can match a lot of things. It's quite powerful, actually. In F# we have something called active pattern. You can declare a function that can return different values. And that means that when I call match here, then that function will be called, and the result of that function is what will decide which branch of the matching expression we execute. Here we have even or odd, so that is called from the match, and the result is, let's say it's even, then that even will match, and we print X is even. This is very powerful because you can have very complex matching used in this function. You can have return variables and a lot of things, really. I haven't found any way to do that in Rust, actually. There might be. Another thing is error handling. In Rust, there are no exceptions. There is one unrecoverable error, kind of an exception, that is panic. If that happens, we crash. We can't recover from this error. We're going to say we're going to read a file and do some computation on the data in that file, and we can't even find the file, and it's pointless to continue. Then we panic and crash. Instead of exceptions, Rust uses results everywhere. That is, every function returns a result indicating if it was a success or a failure. We will look into that. In F#, there are exceptions because .NET has exceptions. We have to try catch or try web, as it keyword showing in F#. And if we don't catch an exception, it will crash. But as F# developers, we like to use result instead as well. In Rust, a result is an enum with two values, OK and O. So, like if we try to open a file, that will give us a result back. and we have to match that result with, was it okay? Well, then we got the file and we can do what we want to do with that file. Or it was an error. It could be file not found, or maybe access denied, or something. We couldn't open the file. There was an error. Then we have to handle that. So if we want to read data from a file, we have a function here that read data from file. It will return a result string, that is the data we want to read from the file, or an IO error. We couldn't read the file, there's an error. So the first thing we do is we open the file, then we check was it okay or error. If it was error, we return here, return that error. There's no point in continuing. If we couldn't even open the file, then we can't read it. So return if there's an error. And then we declare a string content saying that here's the variable I want to use to have my content. And I'll do file read and tell it, put the content on the file into my variable content here. And if that went okay, it might fail to read. We have to handle that. If it was okay, well, then we have content. If something went wrong when we tried to read a file, we return an error. And there's underscores on some of the text here. My editor was kind enough to underscore everything that's mutable. So you could see that mutable variables here are underscored. This is a very common pattern that you do something, get a result back, you check was it okay or error. If it was an error, then we exit. And then we do another thing, check it was okay or error, and so on and so on. So a very common pattern to do this. Do something, check was it okay or error. Do the next thing, was it okay or error. It gets a bit tedious, perhaps. So in Rust, you can do a shortcut. Here we have the file open, and then we have a question mark at the end. That means if this the result from this call was error, then we will return immediately. If it was okay, then it will continue. So if file open returns okay, and we got the file, and we can declare our content. We can read the file with with a question mark at the end, meaning that if it fails, it will return that error. So if we get to the last line, okay, content, then everything worked. So we have our content and we can return that. So that's a nice feature in Rust. You can do shortcutting like this. And you can even chain that. So here we open the file, have a question mark. If it fails there, it will return there. Otherwise, it will continue. Read to string, question mark. Did it work? Yes, then we can return the content. If not, it will return the error. So that's a nice way to shortcut the matching of OK error. Right? In F#, we need to handle exceptions. So a file open here could throw an exception, and the exception could be file not found or access denied or something else. We need to handle that. So we try, open the file, and if something failed, well, we print them and the error message, and we throw or erase the exception again to someone else to handle that. But what we really want to do is use the result here as well. So here we have the read data file. We take a file name, And this function will return a result of string, that is the content of my file I wanted to read. And the second string is the error message. So here I open my file, I read the content, and then I return it. Everything went okay, and here's the content. And if there's an exception, I return error and a message. So we've wrapped this error handling, the exception handling in a result function. So that's the way, at least the way I like to do it. There are other ways to do it, but I like to do it like this. So we can now have a result instead. I read the data from file, I will get the result back, and I have to match on that one. Was it okay? Then I can print it. If it was an error, then I have to handle that error. In F#, there are a way to shortcut this as well. What you do is that you declare a result computational expression, is the term, but it result block, really. And here we have let and an exclamation mark. So let bang, we call it. That means if read data from file returned okay, then content will be set. If not, we will return immediately from this function. So in Rust, we set a question mark at the end of a statement. In F#, we set an exclamation mark at the beginning. But it works the same way. It shortcuts. If it fails, then it will return. If not, it will continue this function. Another thing is higher order functions. A higher order function is a function that takes another function as a parameter or returns a function as the result, or both. In Rust, we can declare lambdas. That's really easy. We can have a function that has a parameter as function. We can do that as well. It's a bit clunky syntax, I think, but it's quite doable, no problem at all. But when you come to having a function as a return value, it's possible, but it gets really complex because of the memory ownership and memory management. We'll look into that in a while. In F#, everything is easy regarding that. Declaring lambdas, no problem. Parameters, no problem. Function as return values, no problems. We don't have that memory management we need to handle. The garbage collector will take care of it when we're done. So in Rust, we can declare lambdas. Let's say we have a vector of 5 numbers. We want to iterate over that vector. And for each number, we call map. That is, we call this lambda, that is x as a parameter, and it returns x times 2. It multiplies by 2. And then we have a filter. We only want values that are greater than 5. And finally, for each result, we print it. And here's a quirk in Rust. The larger than operator, less than also takes a reference as the second parameter. I don't know why, but that's the way it is. So the filter x larger than has to be a reference to something. So it has to be a reference to 5, which is a constant. And that's a bit surprising, but that's the way it is. And we can do the same thing in F#. We have this array of 5 numbers. We call a lambda that multiplies it by 2. We filter then with a lambda that filters out everything that's bigger than 5. And finally, for each value, we print it. Same way, same thing. Syntax is a little bit different, but it evaluates to the same thing. If we want to have a function as a parameter, we can do that in Rust. Here we have binary operator function that takes 3 parameters, takes n and m and an op. An op is a function that itself takes 2 integers as parameters and returns an integer. So here we need to declare binary operator as a template function and have the type of the parameter as a where. It works. It's a bit clunky, I think, but there's no problem with it. So we can call binary operator 2 values and a function that we want this to execute. So first we do it with add, and then I do it with multiply. Given that add is a function that takes 2 parameters, takes 2 integers and returns 1, multiply the same. So it's doable in Rust. A bit clunky, but works fine. If we want to do that in F#, that's it. We just declare that binary operator takes 3 parameters, and the result is op and x and y. That is call op with x and y as parameters. That's it. Not much more to add about that. If we want to return a function, then it gets a bit complex, because we have to take into consideration who is owning the parameters to the function that we are going to call. So you have to add something, this tick A, which is a lifetime that tells the compiler that these values all belong to the same lifetime. So when this value goes out of scope, all these values should be removed. I'm not going to go too deep into this, but it gets hairy quickly. But basically, we call unapplied binary operator with 3 values, 2 constants, and a function that we want to execute. And we get the function back that we can execute at a later time. And that is what gets it a bit hairy. Who is owning the data that we have during this time? And then finally, we call that function and we get the result. So it's doable, but not easy. In F#, well, it's just easy. We return a function, now do this, and we're done. So in that case, F# is much easier to do, just because we don't have to take care of the memory. Who is owning the parameters? Who is owning what? We don't care. The garbage collector will fine do it for us. Another thing is partial application and pipelining. Both languages support partial application, pipelining as well. F# supports it by default. In Rust, you have to add an external package to this. So partial applications, you can say that add5 is a function that takes 1 parameter, x, and what it does, it adds x and 5. Double it is a function that takes 1 parameter, it multiplies x with 2, and print it. Yeah, it prints the value. Then you can declare a pipe or a pipeline that starts with an 8, then calls add5 on that one. The result of that will be used when calling double it, and the result of that will be used when calling print it. So we take 8, add 5, double it, print it. Nice little pipeline that's easy to read and easy to understand what actually happens. We can do the exact same thing in F#. We declare add 5, the double it, and the print it functions. Then we declare a pipeline, start with 8, add 5, double it, and print it. Exact same thing. If we look at async, in Rust, we declare functions as async, and then we call await to get the result. In F#, we wrap it in an async block, not an async computational expression. And then we use let bang, do bang, and return bang to await the results. In Rust, it looks like this. We declare async function. We do stuff. Here I call sleep for 1 second and do await on that. So we wait for 1 second and then we calculate the result. And now we can call do stuff in my function here, something, and then we await the result. So it will take a second before that result is done, and then we print it. Quite easy to use. In F#, we do it a little bit different. We declare an async block, or an async computational expression. Here we do, because async sleep does not return anything. We don't have anything to check against or handle the results. It's just do this. There's no return value. And as we do exclamation mark inside an async block means await the result. We sleep for a second and return the result. And in something we do an async block, we use let exclamation mark, that is await the result of do stuff 42, takes a second, and then we can print it. So we can do async in F# as well. It's a little bit different, but mainly more or less the same thing. So what we have seen is that both languages has similar syntax and features. What differs is the memory management. That's the big thing. If we look at tooling, both languages have strong support in VS Code and other editors as well. Rust, I would say, has a steeper learning curve due to the memory management. That takes a while to wrap your head around. And thus, F# is a bit easier to learn, especially if you're familiar with functional programming. Rust has a growing ecosystem and packages. Rust is becoming more and more popular now. F# has a huge existing ecosystem. I mean, .NET has been around for, 23 years now. There are packages for everything. So it's a huge ecosystem. Rust has a growing, vibrant community. F# community is smaller, I would say, but very passionate. So when would you choose one over the other? Well, if you have a use case that is tight memory, very performance critical IoT device or smaller computer or whatnot, Rust. Definitely choose Rust. That's what Rust was meant to do. So that's what you should do. On the other hand, if you have big data, a lot of complex data structures and data analysis, F#. because that's what F# was meant to do. But life is never this black and white cases. There's always a grayscale. So when do you switch from Rust to F# when you move along this grayscale from small devices to big data? I don't know. It's more or less up to you, really, or your team, your current infrastructure. If you already have .NET runtime in your system, then maybe F# is better choice than Rust, and the other way around. If you don't have .NET runtime, then maybe bringing the .NET into your system might be a big step. Might be better to use Rust instead. But it depends. And I would say it's up to you. You have seen they are quite alike in their syntax and features and how you write things. It comes up to the ecosystem you want to have, really. In my case, I would probably choose F# over Rust more often than the other way around, mainly because I am comfortable with F#. I've written a lot more F# code than Rust now, and I just prefer F#. That's my thing. So that's it. Thank you for listening. And if you have any question, just let me know.
Thank you very much, Johan. Thank you for your presentation. We have a question immediately in the chat. I
Yeah.
assume to you, Johan, I assume you have done quite a bit of coding in C# also. Do you have
I
some
have, yes.
personal experience regarding any benefits switching from C# to F#?
Yes, as I mentioned, quite a lot of, or a whole category of bugs just disappears when you do functional, when you go F#. All those cases where you missed to handle a case, you can't do that because the compiler won't let you. So runtime errors almost never happens when you do F#. So yes, I would say it might take a little longer to write the program, but if it compiles, it works.
Yeah.
That's my experience.
Agreed. Another question for me, it's maybe not F# versus Rust, but more, you mentioned Rust being smaller. I mean, I seen comparison on the internet, I don't know, but still is C, I mean the old programming language C is still relevant for really small devices? Or when
Yes,
you're super memory constrained?
Yeah, it is, but I think Rust is growing in that department as well, because it can be very, very memory tight, and you have very good control of the memory when you're using Rust, and you get the compiler helps you a lot. So it's very, very difficult to shoot yourself in the foot, which you can easily do in C.
Yes. Anyone coded in C knows that it's it's very easy. People are just thanking you in the chat for your very nice presentation. So thank you very much, Johan, and for your nice presentation. F# versus
Thank you
Rust.
for having me.
Yeah. Okay. Then thanks you very much, Johan, for your presentation.